Hi, I'm Reza Taimuri, the lead developer of STE software, and in this video we are going to talk about 1D river modeling and drawing cross sections. When we talk about 1D river modeling, everything starts with cross sections, and drawing cross sections sounds simple until you actually try to do it properly. In most workflows, you have to manually draw each cross section perpendicular to the river center line. That means checking angles, adjusting spacings, and constantly zooming in and out to make sure you're not introducing geometric errors. Now let's add reality to the picture. Rivers bend, they widen, narrow, split, and reconnect. Keeping every cross section truly perpendicular to the flow, to the local flow direction, becomes slow, repetitive, and honestly exhausting, especially when accuracy matters. And accuracy does matter. A slightly rotated cross section can change hydraulic properties, affect conveyance, and quietly degrade your results without warning. This is where STE changed the experience completely. In STE, drawing cross sections is no longer a tedious GIS exercise. The software understands the river geometry, automatically handles orientation, spacing, and alignment, and lets you focus on the physics instead of fighting the geometry. What used to take hours becomes something you can do in minutes, more accurate, more consistent, and yes, actually enjoyable. In the next part, I'll show you how STE turns cross-section generation into a fast, precise, and effortless step in 1D modeling, and how to export the drawn cross-sections and import them in HEC-RAS software. The very first thing we have to do in this regard is to draw our river line or streamline. For this case, you can use the automatic tools inside STGIS, or just draw it manually yourself, just how I'm doing it. For spanning, while you're drawing a line inside the STGIS, you can simply press space, just like HEC-RAS software, which in that software you press shift, but in STGIS we press space for temporarily switching to pan. Okay, for saving this shapefile, I simply press save shapefile, and the drawing is finished and data is saved. So I go to the cross-section extractor tool. In this tool, you see I have to choose my streamline. There are 3 different methods that I can select to indicate how I'm going to distance between the cross sections by a specific distance between each cross section by vertices. In this case, software will draw a cross section where the vertices are along the line. For example, if we choose this method, we will have a cross section on the point 1, on the point 2, on the point 3, and so forth. So if we select by vertices, we have to determine vertices step, which will draw a cross section on the first, on the second, on the third. If I change it to 2, it will leave the second one without a cross section and go to the third one. So there is another method which is by count. You can select a specific count which will determine how many cross sections will be drawn along this polyline streamline, and that will tell the software how much distance should be between these cross sections. So I select by vertices here because the vertices are spaced just fine along this river. What I have to choose next is max cross section lengths, which determine how long should a cross section be in your project. By default it is 250 meters. I change it to 2,500 meters, and I simply press on compute, and you see the cross sections are delineated on the map, nice and tidy. Okay, this is the simplest method which we can have our cross sections. As you see, there are somewhere along the river line which the river become narrow, and we want to make these cross sections match the overbanks. For this, in this regard, we can use the right boundary and the left boundary. So let's draw our right boundary. If the flow is going this way, the right boundary will be this side of the river, and the left one will be this side of the river. For each one, I'm going to draw a line boundary. So this is the right one. I simply name it right. Let's go from here, start from here, and draw the right overbank boundary line. So this is our right overbank line or right boundary line, and make sure you have continue it long enough to make the cross section cut this line and stop here. Okay, I need another line for the left side. I simply name it the left and start drawing it as I did for the right one. I'm fine drawing, and this is our right boundary line and this is our left boundary line, and again we go to the cross section extractor tool. With the by vertices method, we just select our right boundary line and then the left boundary line and simply click on compute, and you see the tool just modified the cross sections to cut the and stop where our boundary line are dictating. And we see there are some cross sections which didn't arrive to the right line or maybe the left line. This is because our max cross section length is not enough. I set a very large value and we see the problem is solved now. So our cross sections are ready for this reach, and we can use it inside the STE software to simulate water flow or extract it, export it to softwares like Hecras and use it there. For example, for using these cross sections inside the STE software itself, we can use manage cross sections to see the data set for each cross section. For example, you see for the cross section, for the first cross section, we have no data inside it, but we have a DEM underlying it. We can extract data easily using STE-GIS by right-clicking on the table and go to the get elevation values from DEM, and for all cross sections I simply select the DEM raster and press OK. It will get the data from the DEM underlying the cross sections and show it to us here, just like this. We could make the cross sections longer to get the overbanks completely by simply moving the right line and the left line out and give it more space. Now we have the data here on the cross sections. We can simply click on save to save the data on file, and now go to the next steps, which can be Grid Forger for creating DEM using the data underlying these cross sections, simply by selecting the cross section and using cross section data and click compute. It will create a raster just by using the data set for the cross sections. The other use we can have here inside STE-GIS is cross-section analysis, which will analyze a cross-section hydraulically by selecting the cross-section file and selecting the desired cross-section. For example, here I select this one, and by selecting the hydraulic model, a friction slope, which can be variable or constant value, and we can even analysis sediment transport here, which I will create another tutorial video for this one later. I want to do a full bank analysis with a precision of 100 rows, which will make my analysis more accurate and with more details. And I simply have to click on analysis to see how is the flow behavior inside this cross section. I can see the changes of flow velocity along the cross section in lateral by simply selecting my desired flow depths. I can see how flow and water is filling the cross section. I can see the variables of area, mean velocity, wetted perimeter, top widths, and so forth, hydraulic radius, and the flow velocity changes in lateral. And I can have these values inside Excel as CSV wherever I want to save them, and I can have the stage discharge relation very easily. I can see how water behave in flooding situations in this river by using river flow analyzer. I simply select my DEM. If I have a manning region raster, I can set here, which we will create another tutorial video about how to create a manning region raster. Here I use manning value, constant value of 0.06, and I select my cross sections. A WSS file is so necessary here to be created, otherwise the software will use the riverbed surface slope for the hydraulic calculations, and we can couple 2D, which software will go and compute the flood extents and flood depths outside the 1D area, which is inside the cross sections. There are two methods here, which one is implicit and explicit. I simply use the implicit method, and we can draw an area of interest, which will lower the computational cost for the 2D area. I simply select click on the next without changing the parameters here, and the calculation of the 2D area will begin, and we can say it's enough. It will affect the accuracy of the calculations if you don't let the derivative tolerance to be satisfied. As you see, the river can be analyzed for different flow depths at the beginning and at the end of the cross sections by lowering and changing the position of these leverages. I can see how the inundation, flow depths, and other parameters here changes, and I can use high accuracy flow routing for more flow routing computations, and I can simply create a flow depth map using this tool. Okay, these were just a demo of how we can use STE in 1D computations. A more detailed video tutorials will be created for each of these tools later on our STE School YouTube channel. Make sure to subscribe this channel for staying updated and watch our new videos. Okay, let's see how we can export these cross sections that we easily created and bring them to the HEC-RAS software for more 1D simulations at that software. In this regard, I have to notice that these files which are shown in red are saved temporarily, and if I want to make them permanent, I have to select them first, which I need for HEC-RAS is my streamline and my cross sections. I have to select them and right click and click on make permanent copy file and make them permanent by giving a name to them and for cross sections, and give them a directory, which I select here and click on run to make them permanent. Okay, we are done with STE. We now have to go to HEC-RAS. Okay, I open the HEC-RAS software. I simply create a new project. After I created my RAS project, I simply go to RAS Mapper. Inside RAS Mapper, the first thing I have to do is to set projection. For setting the projection, I can simply use one of the PRG files created for the river line or the cross sections and click OK. Okay, now our RAS Mapper's projection is set, and we can add our DEM to the software like this, and the terrain is created using the DEM. We have the terrain here. What we have to do is to create a new geometry, and the geometry goes like this. What we have to do is to start editing the geometry. In the rivers, we have to import the river line we draw inside STE. I simply click the select the file river.shp. Okay, sometimes Hecras will fail to load the data which we created in STE software. That is because the file is open inside STE. We have to simply close it and get back to Hecras. In most cases, it will be able to open the file when we close the file there, and the data will be added to Hecras. We just click on import and we see the river line is imported successfully to the Hecras. Now for the cross section, we can right click and do the same import features and open the my.crs file which have the data of our cross sections, and click import, and we see the cross sections which we created in STE came to Hecras and we can use them. Thank you for watching this video. I hope it was helpful and gave you a clearer view of how STE makes 1D river modeling simpler, faster and more accurate. If you found this useful, please subscribe to our YouTube channel to stay updated with upcoming tutorials and new features. There are many new tutorial videos on the way and we're excited to share them with you. See you in the next video.